So first, I would like to warmly thank the organizers, Christophe and Emmanuel, for putting this school together, and all the very hard work to make it as we can enjoy it now. And of course, this beautiful setting that is really quite an inspiration to work and to share between us. Also the opportunity to meet many young researchers and share our work. So my lectures will concern the water wave problem, and the philosophy about it is about this Hamiltonian character. So I should acknowledge my long-time collaborator. I had many collaborators, but two of them were my long-time with whom I've worked. Philippe Guyenne and Walter Craig. Many of you probably know him. He very sadly passed away 3 years ago, but he was really an expert in Hamiltonian PDEs. And Philippe Guyenne is a professor at Delaware University. And he's really an expert on numerical simulation, in particular the numerical simulation of Euler system. Okay, so today, I will, this is the outline. I thought I'll say a few words about the outline so we know where we're going, as you know, some calculations are kind of complicated. So first of all, I will present, of course, the Euler system for free surface wave, and I will benefit from the presentation, very beautiful presentation of Robin. So, in particular, the physical derivation from Euler, that I will just repeat just to clarify my notation, and the particular, this very special property that was discovered by Zakharov in '68, that indeed the water wave system enters into, can be recast as a Hamiltonian system. So that was, it is not a simple observation, and it will take me some time indeed to prove this, to prove that indeed this problem can be recasted as a Hamiltonian system with findings, explaining precisely what are the canonical variables and what is the Hamiltonian. So the Hamiltonian will be naturally the total energy. The canonical variables will be also quite natural once you know which one they are. In particular, one will be the surface elevation. And in this formulation of Hamiltonian Hamiltonian formulation, what happens is that the original problem is replaced by a system for variable defined only on the surface. So somehow going from a problem on the full domain to a problem only restricted to variable on the surface comes from solving a Laplace problem, and there will be, of course, non-local operator. So the non-local operator that will be at the center of all this discussion is called the Dirichlet-Neumann operator. And just to know what it refers, even although I will be much more specific later, if you have a domain, it will be not the fluid domain, because the fluid domain is different, but imagine you have a Laplace problem here in a domain with a Dirichlet boundary condition, and you are interested in the correspondence from the Dirichlet to the Neumann derivative on the boundary of the domain. Okay, that's the domain D. And this operator, this called Dirichlet to Neumann, will be central in the whole analysis. And it has been studied in details by many analysts, in particular Thomas Salazar, David Lann, and many others. So some of there are many properties. Some are basic. We can prove it on the blackboard. Some are more complicated. But it is important because it appears naturally in the formulation of Zakharov. And if we want indeed to prove that this water wave, that it is indeed Hamiltonian, we will have to do some variational derivative of the Hamiltonian with respect to the variables, and in particular we will have to discuss what's called the shape derivative. Essentially, what happens to this operator when we modify a little bit the boundary. Right? So it's what's called the shape derivative. Okay, and so there are a number of properties of this Dirichlet-Neumann that we will consider, and then after this I will concentrate on the application of perturbation of Hamiltonian system to derive some fundamental equation obtained, as we have seen this morning, in various important scaling regime. So in particular, Boussinesq or Korteweg-de Vries in the case of long wave scaling. And using Hamiltonian transformation theory to derive this equation. Now, there is the aspect of formal derivation that I will explain. There is also the important question of how the validity of this derivation, in particular, rigorous result that to validate the derivation. So how good is the approximation of the solution obtained from the model equation compared to the solution of the original problem? So that's a difficult question, and for this I will essentially state the results. I will probably not be able to give the details. That's too complicated. And then, in the spirit of this Hamiltonian transformation theory, I will introduce what's called Birkhoff normal forms. So essentially, we will be interested in small solutions, long-time small solution, if you like, and we would like to develop a method to eliminate terms that are somehow non-essential. So that's the idea of Birkhoff normal form. You have a difficult problem and you want to eliminate terms. You cannot eliminate everything, but you just want to keep the most significant to describe this nonlinear evolution. And for example, maybe some of you know, just to make a relation with something maybe more familiar, there was a paper by Jalal Shatta in 1985, and it concerned the Klein-Gordon equation with quadratic nonlinearity. Okay, quadratic nonlinearity, and the method that he was proposing is to make a transformation. He called that normal form transformation, that transforms this Klein-Gordon that was f of UU, right? Quadratic nonlinearity. By a transformation, he would, by a change of variable, he would transform to a new equation with cubic nonlinearity. And cubic nonlinearity would allow him to get description for long-time behavior. So it will be in the same spirit. We will have from the Hamiltonian, we will have an expansion of the Hamiltonian in small parameter, and we will try to eliminate terms of, we will go only to fourth order. And so I will try to explain to you the procedure, in particular this transformation at the level of removing cubic Hamiltonian, and also a very beautiful result that was originally proved by Zakharov and Dayachenko. That was, and at the same time, Craig and Wolfok. That was essentially at the same time, 95, where they proved a certain notion of partial integrability. And interestingly, that was completely formal, but recently there has been papers that validate and prove this partial integrability. So again, the proof or the rigorous is very complicated, but I think it will be interesting to mention the procedure. It's essentially by a group of people, Berti, Feola, and Pusateri, and that's relatively recent, 2021. So I'd like to discuss this partial integrability, partial because it's only up to order 4. And then I would like to apply this Burkhardt normal form to the derivation of the nonlinear Schrödinger equation. So earlier we were talking about derivation of KdV, and another important equation that comes as an effective equation for in certain asymptotics is the nonlinear Schrödinger equation. So we will derive NLS from directly from this theory of Hamiltonian perturbation, and I will also like to show you a higher order NLS. It's called dist equation, and there is two aspects of it that I would like to share. One is that in the applied community, the dist equation seems to be better than just a simple NLS equation, especially to model waves that are of higher amplitude or steepest. And the second is that in the original dist equation, obtained by Dist, in fact, in 79, the dist equation was not Hamiltonian. In a sense, dist is not as universal as NLS, so there are several versions, and the effort here was to derive a dist equation that keeps the Hamiltonian character. So by this derivation, it comes automatically. So after this, I would like to, this is the, I hope I will have time to discuss the initial value problem for the water wave equation system. It's, of course, a difficult problem, local existence, global existence. I will not be able to give the details, but at least some description of the results and some important aspect that comes into this analysis. In particular, what's called the Taylor sign condition that was already known for a long time, that if it concerns the water wave problem and you linearize near a particular solution, not the zero solution. And if you want to have this linear problem well posed, you have to assume that there is a certain quantity that has a positive sign. It's called the Taylor sign because it goes back to Taylor, the the fluid dynamics scientist. And so I would like to show this, how this Taylor sign condition comes up in the local and global well-posedness. Okay, and if I have time, but not sure, I would like to present to you a more applied problem where the question is to understand the coupling between internal and surface waves. So internal waves are waves that propagate inside the ocean. They are very common in many places, everywhere in the oceans. And they are important because they have all sorts of effects for all sorts of applications. But in this setting, we would like to understand how their effect on surface waves. So there is a list of things that I would like to show you in particular. I will probably do that with slides because otherwise there won't be really time to. So I'm not sure we will have time, but the physical problem in particular, and then the modeling, which consists in assuming we have two fluids, for example, one cold and one hot, and the internal wave is essentially materialized by the separation. So this happens in tropical seas, for example, or when you have the two seas like Mediterranean and Atlantic meeting, because we have the more salty and less salty. And I would like to maybe show how to derive a system for KdV describing internal and a linear Schrödinger describing the envelope of the surface. So we'll see if we can get there. And in this setting, I have many references. They are not absolutely, they're probably many references are missing, but when Tian Tai and Raham write the notes, we will add the reference when needed. Okay, so this is the end of the general discussion, and I will turn this off. Thank you. And start. Right? So, can I raise? If there are no question about this long introduction, I will just start. Right? Okay. So the water wave problem. So we try to be organized, and I will so the physical derivation. From the Euler. Okay, so the fluid domain, we call it omega of t. We will mostly work in 2 dimensions. So this will be the bottom at the level y equals minus h. And this will be the surface elevation that I will call eta, the function of x and t. So the domain omega. So x will be the horizontal dimension. And so d is 2 or 3, but effectively, because of the complexity of the writing and everything, we will essentially concentrate on d equals 2. The bottom, it will be minus h. It could be finite or infinite. And yes, so this is a domain, and it is a graph. So there is, of course, a formulation in Lagrangian coordinates that allows the curve to turn around. But just for simplicity, we'll stay with this assumption. Then we have the gravity. The fluid is submitted to the gravity, and we will call u of x, y, t the velocity at time t, function of x, y, and finally the equation. So, like this morning, divergence free, that's the incompressibility. We will assume again, like this morning, that irrotational. It's a hypothesis. I mean, there has been a lot of new results without this assumption, but for today we stay like that. And finally the Euler equation dtu plus u. So minus 1 over rho. Well, rho is a density. It is constant. The pressure minus g. Okay, so in the following, g will be 0 and minus g. So g alone, it's positive. Right? So this is the Euler equation. And immediately from these two equations, we will have the velocity potential phi that satisfies Laplacian phi equals 0 in K of t. So the gradient phi equals u, and in terms of the velocity on the velocity potential, this equation becomes gradient. So I put all the derivative outside. Dy equal okay. So that's the equation in omega. And then we can get rid of this. We can get rid of this gradient, saying that the whole expression is constant in time, and this constant in time can be. So I revise this. It can be absorbed in phi. So at the end, we will have inside the domain the pressure divided by rho plus gy equals 0 in omega of t. Okay? So that's the Euler equation inside the domain. And of course, the boundary condition, as we have seen this morning. So at the bottom, that's the condition of Euler. The normal derivative is 0. So normal derivative is the normal component of the velocity. No, sorry, the normal component of the velocity is 0. So that means so u dot n equals 0 on y equals minus h, which means normal derivative of phi. Okay, that's a classical one. And we saw also this morning two boundary conditions on y equals eta of x and t. Okay, so inside we have Laplacian phi equals 0. Downstairs here, Neumann. And of course, all the nonlinear aspect of the evolution comes up in the boundary condition on the top. And as Robin showed this, explained to us this, there is a kinematic. Kinematic tells us the surface moves with the flow, right? It moves with the flow. So we can write it if, well, I think it was this morning, but I just copy it again. If we consider the expression y minus eta of x and t, and we call this f of t and xy. Okay, so this from this function f, we're just going to write that the total derivative in time of this function equals 0, restricted to y equals eta of x and t. Okay, and if we do this, we find exactly the condition that we had this morning, which says that eta of eta t, so I just don't do the calculation, but it's evident from here. Minus, so the condition eta t equals, just make the minus, plus phi x eta x minus phi y. Okay. Another way to say it is that the normal derivative of the velocity and the normal derivative of the interface are the same. So that's the equation that comes always. That's on gamma of on y equals. And the second, so that's one, this is kinematic. And the second one is dynamic condition. And as we saw this morning, it's called the Bernoulli balance of forces, that essentially tells us that on the surface, on the surface elevation, the pressure is constant, equal to the atmospheric constant. So P equals and I forgot to say that I have neglected surface tension, but if there is surface tension, but we will not consider it, but just as a remark, if there is surface tension, then P on the boundary, P minus PA is equal to, so this is a coefficient that measures the surface tension and multiplied by kappa, which is the curvature. Okay, but I don't need to write it because I will neglect this term. Okay, and so this is in this case we now evaluate this equation. We evaluate this equation at the border, at the interface, and we get dt phi. So dt phi plus, just copy this, plus g eta, and equal minus P atmospheric. And we can assume, we can absorb this constant into phi, so that can be chosen to be 0. So that will be the second equation. So we have a system composed of, so let's put it, so I don't copy it again. We have this equation. We have this. Although when the bottom when the domain is very deep, that will be replaced by phi tends to 0 and uniformly in x. We will not worry too much about that. Then this is this equation. and that one. So this set of Laplace problem plus these boundary conditions is what are called the system of water wave, the water wave system. Okay, so I suppose that's known from many people, but that's our starting point. And then I will just repeat what Robin said this morning, just because we will need them later. I'm going to list three invariants of motion: the total energy, which is the kinetic plus potential, the conservation of energy, conservation of mass, and conservation of momentum. So these three invariants can be derived directly from this equation. I will not prove them today, but later, when we will have in hands the Hamiltonian formulation, they will come automatically from Hamiltonian theory. Okay. So I will just, but it is important to state them because they will be our. So this the energy, I'll call it H because it will be our Hamiltonian later. It will 1/2. Okay, let's put the 1/2 gradient phi plus G. Okay, so that's the kinetic energy, that's the potential, where eta is the elevation. Then we have the mass, so that's the total energy. We have the mass, V or integral. Okay, and we have the momentum, I. So it's a horizontal momentum. It's integral over R of integral over R of dx eta phi dx. So if this is 1D, so this is 2D, so this is an integral over the horizontal variable. If D equals 3, so the horizontal variable has 2 dimensions, then we would have I1 and I2, where we have here dx1 and dx2. Okay, so but here we have only one. Okay, so this is the derivative respect to x of the elevation, and then multiplied by the velocity potential restricted to the surface elevation. So later we will recover this invariance. Okay. All right. So that was the physical derivation, and now I would like to state the Zakharov formulation, that Zakharov Hamiltonian formulation. And this Hamiltonian formulation has been used for many purposes, analysis, numerics. You will see. I'll show you how it can be used very effectively for numerical simulations. also for asymptotic derivation, as I will show later. So I liked to, of course, to state it, but also to prove it, so it's not just a black box. Okay, so that was a short paper. A short paper, I think 6 pages. There is a Hamiltonian. There is the NLS derived from the as an envelope equation. So it's a very compact paper. So to be able to describe this, we need a Hamiltonian and we need the variables. So the Hamiltonian is going to be exactly this. Will be H, okay, which is exactly this quantity. And the variables, so the variables will be variable defined only on the surface. And there will be, so there will be two variables, eta, which is in fact the surface elevation, and the second one, we used to call it xi, but some people call it psi, depending on what you like as notation. It will be the trace of the velocity potential on the trace on the surface elevation. Okay, and so Zakharov Zakharov result says exactly that. If I take, so that's maybe I should say it. It's a theorem. The water wave problem can be recast into a Hamiltonian system for with Hamiltonian H with Hamiltonian H and Darboux coordinates eta and xi in the form that I write upstairs. So dt of eta xi equals 0, 1, minus 1, 0. So this matrix, often we call it the symplectic matrix J. And here, the functional derivative, the variational derivative of H with respect to these two variables. Okay, so it's a very nice result, but it's quite cryptic in a sense because we need to understand what is the variation of H and the variation of H with respect to a small perturbation in eta and a small perturbation in xi. So it is not absolutely trivial from this how we can calculate the variational derivative of H and with respect to phi, to xi. In fact, it's not phi, but it's xi. So to prove this result, I would like to do it in. We're going to do it in several steps. So I will write the steps so we know where we are. First, some of the steps will be easy, and the one will be not so easy. So the first one is to return to the definition of H in term and write it in terms of these variables. Well, that will not be too hard. We'll do that. Then the second part, the second step, so we don't forget what we're doing, it would be good to, since Sakharov gives us these variables, we should be able to, from our system, from our original water wave system, so from the water wave system, write the evolution of the two variables d. Okay, so we'll have a system. Then I would like to just to make a remark to explain where do this variable come from. Because, of course, it is very natural to take as one variable eta. It's the elevation. It will play the role of an angle variable, and how to get the corresponding action variable. So the argument is returning to classical mechanics, principle of classical mechanics, and we will see by a simple argument that if eta is the angle, then xi, that one should be the conjugate. Okay, so it doesn't look too mysterious. And finally, we need to identify. So if I call F1, F2, just for, we should identify F1 and F2 to the derivatives, to the functional derivative, to the variational derivative of with the right sign of h respect to the variables. So that part is not so easy. In particular, this one, because this one will essentially we need to understand how this total energy changes when the domain is changing. When we do a small perturbation in eta, everything changes. But so that will be a little bit more delicate. But I think it's an important thing to understand. Otherwise, the whole thing becomes just too mysterious. Okay, so that's the program. Okay. If you have any question, everything is clear? Okay. So we always start with the not so difficult part. Okay. So what is it? We want to we want to write the Hamiltonian. We want to write the Hamiltonian is here in terms of eta and xi. Okay, so step 1, we want to write h. So it's dx dy, right? Dy dx plus so I write it on omega. Okay, so this is already, we have nothing to do. It's already in terms of eta. So we just have to worry about this term. It will be quite simple. We use the Green's formula. So it replaces this by Laplacian plus the contribution to the boundary. So we have the bottom, d phi dn, phi. Okay, and then plus the integral over gamma of phi d phi dn. So this one I don't touch. Okay, so phi is harmonic. This goes away. This goes away because it's the Neumann. And we are just left here. So this is the Xi, right? Because it's a trace of the velocity potential on gamma. So that's exactly what we defined as this variable. And now we have this d phi dn. And this is where this Dirichlet-Neumann operator comes up. It's because, so let's redo the picture. We have the following problem. Here, d phi dy, let's say, on the bottom is 0. Here, we know that phi is equal to, by our notation, it's the Dirichlet data. And I would like to express d phi dn in terms, assuming that everything is good, we assume that the solution decays at infinity, the eta decays at infinity, everything is well defined. We would like, from this well-posed problem, define the normal derivative. So to Xi, I'm going to associate d phi dn, and on the boundary. So we will always have the Neumann boundary condition downstairs. So to the Dirichlet data, I associate this the normal derivative of this harmonic function. I normalize it by this quantity, which is arc length in a sense, and I call this the Dirichlet-Neumann operator acting to Xi, on Xi. And clearly, this operation depends on the domain. And the only thing in this domain, which is that the quantity that define the domain is this upper surface, is eta. Okay, so indeed we have now a Hamiltonian written in terms of these two quantities, which are quantities calculated or defined on the defined for surface variable defined on the surface. And there is two terms. One is this one, Xi. And because we have defined the G in this way, it absorbs the ds. So this is G of eta Xi. Okay. Plus G eta square. Okay. So this is valid in higher dimension, for a three-dimensional problem, but I'm restricting myself to this. So if this is clear, because we were going to manipulate that Hamiltonian a lot in this week. So if you have questions, please go ahead. So this is the Xi, that's the phi, that's the normal derivative, where we have absorbed this element of surface and the potential energy. Okay? So this is H. Okay? Now the next part is to write this d eta and dxi. That's again that's relatively simple. We just have we have to use these equations here and there. So first this one. So let's see if I can. I need to keep these equations. So if you don't mind, I erase this part except the Hamiltonian. Now, this equation here, we can read it almost immediately from the definition of the Dirichlet-Neumann and the formula. So here we have d eta t equals, and it's not hard to realize that the two terms here identify exactly to the normal derivative. Well, up to this square root. So, so this is exactly g eta of xi. Okay? Because we have the vector n. It's the, what is it? Eta x, 1, right? 1 minus eta x divided by the square root. Okay, so the first equation is the evolution equation for eta that is written here identifies exactly to d eta dt equals in terms of these two variables eta and xi by the introduction of the Dirichlet to Neumann operator like this. Okay, the second one needs a little bit more work, but it's not difficult. So I can now erase this. So we have used Laplacian phi equals 0. We have used downstairs this equation. And now we need to extract from this equation, we need to the evolution of xi. So what is it's well, maybe I don't need to do all the details, but just one or two formulas. It's just the chain rule, but we want to write it all this at y equals eta. And we have also dx with the same okay. And we have g. We will need the Dirichlet-Neumann operator. Right? The Dirichlet-Neumann operator is exactly well, we just said it now. Okay. So from these three formulas, we can solve the vertical velocity, the horizontal velocity. Okay, because we will need them here. We will need the horizontal and vertical velocity. So by we're solving outside from here, and then we have also d phi dt. So I guess we can do it not by in your head, but still, there is a formula for d phi dy that is important. That I will write. It's just by solving this system. There will be a formula for this, for d phi dx, and since we know d phi dy, there will be also dx. So at the end, you do this little calculation by hand, and you obtain expression that will be useful later. This one, which is this in the following week, we're going to call it W. We have another one that can be also expressed. We read it here, so it's dx. What do I write? It's dxc minus so I don't copy, it's just the same W. So imagine we replace this here, and the diffidity again from this where we have replaced the W. Okay, so okay. So finally, this system of equation that was can be explicitly, so we are here, the system, the water wave system is so we have this one, and the second one is a little bit more complicated, G eta. G eta is here. G eta. This one, and that's okay, so we write everything, minus plus, and that's a big expression, a little bit complicated. All right, so these are the coupled system for eta and xi. X is in R. And if we look at it, we see it's a quasi-linear system of first order. It's very nonlinear. If, by chance, if you would like to write it in the case where you are 3 dimensions, so x is in R2, you just simply replace this dx by gradient in x, this by a scalar product. So it's the same system if you work for the 3D water wave. But it's a complicated system, yet it has been used intensively to derive local well-posedness, global well-posedness for small data in certain conditions, not for every situation, but at least for deep water, small data, deep water, small data in 2 and 3 dimensions, deep or not deep water with flat or non-flat bottom by various authors. So in the reference, I will put all the names, but there are never many names. So David Lann, there is Al-Azhar and Burke, Zwilly. There are several work associated to this. That's for, well, there are many results. Al-Azhar, Delors. That's for the 2D global well-posedness. There is Ionescu, Pusateri, the third group, Tatar Wifrim. Well, there is many names, and I cannot write them all, but in the reference they will be there. So not everybody works with the system, but essentially everybody works on a system that is reduced on from the original problem to a problem on surface waves. Okay, so this is this, and I would like to, so let's go to this, where does this variable come from, because I think it's an important an important remark. Okay. So we can remove this. And so from the Hamiltonian expression, we can write down a Lagrangian. So the Lagrangian is written in the form of Lagrangian. So that's point 3. The Lagrangian can be written in the form of the kinetic energy minus the potential energy. Okay? Kinetic is oops, this is 1/2. Okay, and eta, we're going to see eta as the angle variable. And it's convenient to see, to also introduce d eta dt, right? Because I would like to rewrite the Lagrangian in terms of eta and the time derivative of eta, and then using the Legendre transform, define the conjugated variable to eta as being the derivative of the Lagrangian with respect to the eta dot. That's the classical setting of classical mechanics. So here, I would like to make eta dot ddt visible. So I go back to this equation, and I see that formally I can write eta tilde, eta dot. So I can write g eta minus 1 eta dot equals. So of course, g eta minus 1 is not invertible. It has we have the constant that are solution of in the kernel, but we just forget about the constant. Just when it is just formally write this this equation in the form 1/2 of xi. So xi, I write this is eta dot, right? And this is g minus 1 eta dot. And the other one, of course, we don't touch. Okay. And now the conjugated variable to eta is going to be, so it's going to be the action. We're going to see it as dl, the variational derivative of the Lagrangian respect to eta dot. And if I differentiate this functional respect to eta dot, I get g minus 1 eta dot when I differentiate this term, and when I differentiate that one, because g in fact is self-adjoint, I get 2 times. So, but because 2 multiplied by 1/2 is exactly g minus 1 eta dot. So it's not a proof, but it's an incentive to understand how Zakharov came up with these 2 variables. So one being the angle variable is the surface elevation, and the second, by this argument, oh, is this a minus? Sorry, it's a minus. By this argument is xi. Right? So that's how the 2 variables come up naturally, in a sense. So,
so what is the xi? I didn't get that.
What is? xi, because you remember this equation here. So formally, I write xi as eta t, well, I have applied the g minus 1. Okay, so that's how to guess, to have eta dot come up in the formula. And then because there is a 2, I mean, because you differentiate with this one with respect to that one, and g is self-adjoint. So that's the two variables. Okay. Okay. So finally, we need now to identify these two, F1 and F2, so to identify these two quantities to the derivative of h. Do we have h? Yeah. To the derivative of h with respect to xi and eta. Okay. H is the Hamiltonian. I'm going to I should rewrite h. So what is it? 4.4. And okay. So h. Now, these will be my two variables. We'll forget about the velocity potential inside the domain. We have only to work on the so this is our Hamiltonian. Oh, it was okay. Huh? Okay. And so we need somehow to calculate the variational derivative of h with respect to xi and the variational derivative of h with respect to eta. So the easy one is the one with respect to xi, because I see it here. If I differentiate with respect to xi, I have two terms. When I differentiate this one, I get g of eta xi. And when I differentiate this term, g is self-adjoint. We'll see in a minute why. We'll see in a minute the property of g, but it's not difficult to see that it is self-adjoint. So differentiate with respect to xi in the variational sense gives exactly. Okay, that's the easy part. That's the easy part. And so yes, it's back to the first equation. But differentiate with respect to eta, there are two terms. So the second term is g eta. That's the easy one. And well, we see it here. Okay. Minus g eta. But the most difficult part is to calculate the variational derivative with respect to eta of the kinetic energy. Okay, so that will be a little bit more difficult. I think I will leave that part to tomorrow. So we'll spend some time calculating this. Essentially, we're going back to the definition of this term, which is kinetic energy, the integral of the velocity square, and we need to modify the domain. Right? We have the domain, and we want to calculate how this kinetic energy changes when we modified eta by eta plus, let's say, delta eta. At the same time, we keep xi fixed, because that's a partial derivative, in you like, of k with respect to eta. So we'll do that calculation tomorrow. Okay, and we will recover that this term exactly identified to this big expression. Okay, so that's why I'm saying it's not so trivial, because it needs some effort to to calculate this derivative. Okay, so except for this point, we will have done this. Okay. So if you remember the outline, we have covered chapter 1, and well, except for this last point, and oh, I did not do the break, so it's too late. So maybe tomorrow, unless you, well, you can remind me tomorrow that I need a break. Forgot. Okay, so what we need, the next part of this is that we need to do some effort to understand this Dirichlet-Neumann operator. So that will essentially, this is chapter 2. Operator, and now in the coming, now we're not going to write all this, D, N, O, or sometimes D, 2, N, O, something like that. Okay, and well, the first step is not too hard. I would like to, so the basic properties. Well, so the basic property, I mean, it's not too hard, but it's still not trivial. So we're going to start to get familiar with this operator. So I remind you, we have the problem phi . So now there is no time. Eta is a fixed domain on y equals eta. Okay, this of x. So we forget about time, and we have d phi dy equals 0. Okay, and we are assuming this problem has we are in a fixed domain. Okay, that's a fixed domain. That's y equals eta. And this is y equals minus h. And we are interested in understanding the map that to the Dirichlet data associates g of eta xi, that will be the d phi dn of d phi dn modulated by this this quantity, okay? And to get a little bit of sense of what this operator, it's good to start with a flat domain. So we're going to start with a little calculation, assuming that y equals 0. So you simply want to solve the problem. Well, that's something we can do. So we can do explicitly that at y equals 0, so we want to solve exactly this problem, but with eta equals 0. So solving the Laplace problem with Dirichlet boundary condition at y equals 0. Okay, so that's x, that's y. We want to solve the Laplace problem in this strip. We have a explicit formula, and we'll express explicitly also by this explicit formula what g is, g of 0. So I'm sure you all know how to do this. You go to a Fourier space in the horizontal variable, and then you solve for the phi hat in the x variable. And you get that the phi hat, the Fourier transform of phi in the x variable, so my variable is k, because xi is already taken here, so it's not xi, y. It is, so just for simplicity maybe, so for there's no confusion, I'm just going to put it eta, f here. F. So d phi, it's what? It's f hat of k multiplied by. Oh, so I think Robin, you had that formula earlier, but it's okay. Those are the hyperbolic tangent, and then we have the sinh, hyperbolic sinus. Hyperbolic sinus of ky plus cosh, hyperbolic cosinus ky. Okay, so that's explicit. And then one can calculate what exactly we want. D phi dy with a hat of k and y at y equals 0. Calculate, and you find exactly k hyperbolic tangent h k multiplied by f hat of k. Okay, and we can say that this is g0 because eta equals 0 of f hat, okay, of k. Okay, so what do we want if we want to calculate this Dirichlet-Neumann operator for this particular domain, knowing f? Well, what do we do? We take the f, we take its Fourier transform, we multiply by what's called the Fourier multiplier, and then we go back by f minus 1. And what we have obtained through this transformation is, so is Fourier. That's Fourier multiplier. Okay. Equivalently, I'm going to write it once, so there is no confusion. We call it, so what do? I take inverse Fourier transform of k hyperbolic tanh hk f hat of k. But this is a little bit heavy to write, so we will use the following notation. We're going to call d 1 over I dx. So d is this operator. We call it, and if you think in the correspondence in Fourier space, it's multiplication by k. So that's what the notion of Fourier multipliers. So we will write in the following, we're going to say G0 is equal to d hyperbolic tanh hd. That will encompass all this formula, saying that if I apply to a function, it corresponds to a multiplication in the Fourier space. Okay? So that will be, and since we will need this notion of Fourier multiplier a little bit in a systematic way, let me write down here. So this is a Dirichlet-Neumann in this very special case of a flat strip. Oh, by the way, it can be interesting to consider in the case of h goes to infinity, so deep water. This is the case where many theorems have been proved because there is some good simplification. The G0 becomes You see, it's not exactly D. Tangent goes to 1, but it could be plus or minus. So it's absolute value of t. So it's a non-local operator. Okay? It's a non-local operator because you have to go through this back and forth in Fourier to recover it. And even in the deep water, this is non-local, right? Because of the sign. It's like a Hilbert transform multiplied by dx. Okay, so maybe I'll give the definition of a Fourier multiplier because we will okay, so definition of Fourier multiplier. Take a function u from R to R, and we say that M of D is a Fourier multiplier. So if M of D applied to U and all this of X, well, it's exactly this. You take inverse Fourier transform, and this can be done in higher dimension, but I stay here in a and we say it is of order K. So clearly there, it is of order 1. The Fourier multiplier, the Dirichlet-Neumann is an operator of order 1, but it can be of order K if I consider M as a function of K, I differentiate it respect to K, J time. Is smaller than a constant, and 1 plus K squared. So M, no, K is really bad. M minus J over 2. Okay, so that's a definition.
Do you do the lower bound, or?
No, it's bound, upper bound. So, okay, so G0 in particular is a Fourier multiplier of order 1. And maybe I'll stop here, but tomorrow, we will start with a variational derivative of the kinetic energy with respect to the domain, and we'll return to this to the property. We'll return to the properties. So that was the first calculation that with the definition, and we will state. Yeah, so maybe I'll just write it here for tomorrow. We will do the basic property of the Dirichlet-Neumann operator. It's the fact that it is an operator of order 1 in general, from H1 to L2, its properties of self-adjoint, positivity, what else? And we will also show that it is a property that is very non-trivial, that in fact it has a Taylor expansion in powers of eta. So there is an analyticity result that goes back to Kaufmann and Meyer in the 82, but has been extended to many situations. Analyticity of the Dirichlet-Neumann in powers of the elevation, and from this, not only there is a theorem, but there is also formulas. So one can write explicitly the expansion of G in powers of eta. So it will be operators that include other product in the physical space or product in the Fourier space. And this expansion will be the main element to allow us to expand the Hamiltonian in powers of these variables. And from there, you will use it for the derivation of this various asymptotic equation in different scaling regime. So that's so we'll stop here, continue here, this and that tomorrow, and probably more than just the properties will. Yeah. Okay. Thank you. And excuse me? Oh, dispersion relation. Yes, I should have said it here. That once you, good remark. Once you solve this problem, and you know what's the Dirichlet-Neumann operator, you can solve the linear problem, the linearized system. From the water wave problem, you can write down the linearized system near eta equals 0, eta and xi equals 0, right? That's probably what you say, and then from the system you have dt eta equals g of 0, c, and dt xi equals minus g eta. That's all. And so solving, once you have G0, you can solve this explicitly. That means you can find solutions eta of x in the form of a constant, exponential akx minus omega of kt, plus, of course, complex conjugate, right? And then xi, another constant, but it is related, right? And no parenthesis. Another constant related, you can find explicitly the relation. And it is a dispersive problem. So when you substitute, knowing you do it in Fourier, for example, you know exactly the relation that omega square of k, the relation between omega of k is gk hyperbolic tangent hk. Yeah. So that's the dispersion relation. Thank you for asking. And if it were in 2D, you would just have this, right? Absolute value. But from this calculation, you get the important aspect of that it is a dispersion relation. For deep water, it becomes gk. Okay, thank you.